So last time I was talking about cyclic groups. Today I will continue on that as well. So last time we saw that subgroup of any cyclic group is again cyclic. Cyclic group is again cyclic. And this is the first thing. And second thing we saw, if order of A is n, then it implies order of A per k is n by GCD of k and n. Yeah. So today, so these are the things I showed last time. Today we'll see whether there exists a subgroup of order say m whenever m divides n for a cyclic group of order n. And so first let's say suppose there always exists a subgroup of order m for any divisor n of a finite cyclic group of that order. So now the question is whether it is unique or not. So the next natural question is whether that subgroup of order m is unique or not. So there is a second question. So we'll deal with these questions today. So for the first one, it's really easy because suppose G is a cyclic group generated by A and order of A is n. Further, assume that m divides n, that is n equal to m times d for some positive integer t, and let so we need basically an element of order m, right? Because we know that any subgroup of a cyclic group is cyclic. So if we get some element of order m, then we can take the cyclic group generated by that element, and that subgroup will be that cyclic subgroup will be of order m. So so I'm taking that element to be, let's say, so we have a power n is 1, right? Because order of a is n, and n is the smallest such exponent of a such that a power n is 1. That is by definition of order. So we'll take a part D. So let's see what is this order. So this is by the formula that I proved last time. This is this. But now D divides N because of this. So their GCD has to be D itself, which means this is M. So we get an element of order M, and we can just take this subgroup itself. So this is a subgroup, and order of H is precisely order of its generator, which is M. So we always get a subgroup for any divisor of any finite cyclic group. Now the next natural question is whether this subgroup is unique. So let's see. Say suppose there exists another subgroup K of order M. So again we know because K is a subgroup of a cyclic group, K has to be cyclic. So then K will be generated by some element, and any element will be some power of A. So let's just assume K is this, and order of A power R is order of Q, which is M, and it is also this, right? So we get GCD of N and R is D, and that means D divides R, right? By definition of GCD. So D is a common divisor of both R and N. So D divides R. So we can write R as D times K for some K. And this means that A power R is A power D per K. But A power D is in H. So this is in H. So we get that this cyclic subgroup generated by A power R, that is also in H. So this is precisely K. And because both of them has same number of elements, we get that K has to be exactly equal to H. So indeed, for any divisor M, there is a unique subgroup of that order. But for that, we need the group to be cyclic, first of all. So we get this. Yeah. And one more thing that, yeah. So say we know that, say if G is a cyclic group such generated by A, whether there exist more than one generator. So we know by definition A is one of the generator, and let's say G is of order n. So is there any other element that generates G? So if there is, that element must be some power of A, because we know A is already a generator. So if A is so if say G is generated by any other element, that element must be a power R for some R positive natural positive integer. Sorry. So then order of A power R, which has to be order of A, but that is again this, right, by the formula. So we get that this is 1. So it means n r and n and r, both of them are co-prime. And we know that for any given n, how many such elements are there such that those elements are co-prime to m. Those are precisely the Euler free function, right? So there exist exactly these many generators of order so there are exactly phi n many generators of G, right? So there is exactly phi n many generators of G. Uh, but this is true only for finite cyclic group. For example, like if you take the infinite cyclic group, we know we have seen only one example so far, and that is Z, which is generated by +1. But you can also take the generator to be -1, right? Because any integer can be written as, say, if n is negative, then you can write it as n many times. And say if n is uh, positive, then -n is negative. So if n is negative, and if n is positive, then -n is negative. So you can write like this. And so -n is generated by -1, so you can take minus of that element. So that is again generated by -1. So for Z, there are so far we have seen there are two generators. So now the question is, in an infinite cyclic group, in any infinite cyclic group, how many generators are there? So there is another question that you may think about. So I will come to it later. So one thing you can do, you can just take this group and try to find more like a generator that is not one of these. So maybe you will get an idea about how you should proceed for a general infinite cyclic group. And also, by the one thing to note that we have not seen any other example other than this group Z plus. So that is also a thing uh, to keep in mind. So that is these things, and so now I will slightly digress from whatever we are talking about for cyclic groups, and we'll see some particular example of some groups. So far we have seen Z plus and Zn plus for cyclic groups, and for non-cyclic groups we have seen these, right? Also we have seen gln r with respect to multiplication, then we have seen and so all those non-zero real under product, similarly non-zero rational under product is a subgroup of this and so on. We have seen this. So now let's see some. So for finite groups, we have only seen this. So we have only seen cyclic finite groups. We haven't seen anything that is not cyclic. So to start with, first thing that I should have defined earlier, but anyway, so let me define it now. So what is an abelian group? So abelian group means if uh, AB for any two elements AB, for all AB in G equal to BA, then G is called abelian or commutative. Yeah. So let's see some example. So one thing to note that all of them are abelian, right? Because if you add any two integer, the order doesn't matter. Similarly, if you add any two real or rational or complex. But this is not true, right? Because matrix multiplication, is not commutative in general. So you can try to find two example of uh, matrices of GLNR such that AB is not equal to BA. That you should try. So now for any cyclic group, there is an easy thing to see that any cyclic group is always abelian. That is easy because so says G is generated by A. So in if you pick any two elements, that will be some A power K1 and A power K2. And this is just K1 plus K2. But that is same as K2 plus K1. So that is K1. So any two elements are commutating, which means G is abelian. So now the next, what about the converse? Like or like, is there any abelian group that is not cyclic, or both of them are basically same? So for that, we will try to construct another group which is abelian but not cyclic. So let's see how we can do it. So the group that so we pick two elements. Let's say this just denoted by A and B. This is just two symbol. Just treat them as two symbols such that order of A is 2 and order of B is 2, which means A is non-identity, similarly B is non-identity, but A square and B square is same as 1. And so let's see, so we take, so I'm constructing a group of order 4. So there should be 4 elements. So let's see, identity must be there, and also we need these two elements, and because AB is there, their product has to be there because of the closure property of a group. And so you can say that G forms a abelian group. That you should try. That's really easy. Abelian is of course obvious because the way we are defining. The only thing to note is that BA is same as AB. That you should try. But yeah, that's again not very difficult. So why BA is same as AB? Maybe you should, like, let me try. So BA you can write it as, so A square is identity, so you can write PA as E times PA, and E is A square, so it means AB. So E can write it as A square. So I'm just taking one A inside and like this. So I think you should do it from this, I think, or maybe you just need a little bit of manipulation. So yeah, you can take like this, and then, or maybe not this way. So because this is a group of exactly four elements, BA has to be one of these elements, right? Either it is identity or A or B or AB. So if it is A, then you can cancel A and you get B's identity, which is not true. So BA cannot be A. Similarly, BA cannot be B. And if BA is E, that means uh, ABA is A. You can uh, cancel this and you get AB is identity, which is again not true because AB is clearly distinct from the identity element. So that is another problem. So BA cannot be identity as well. So the only option left is BA has to be equal to. So again, this is an abelian group and this is of order 4. And also this is not cyclic because um, why this is not cyclic? So G is not cyclic because it cannot be generated by identity, and certainly it cannot be generated by A and B also because both of them has order 2, and because G is of order 4, any generator must be of order 4. So the only possibility is uh, this G is generated by AB. So for that we need order of AB to be 4. But let's see what is the order. So first, mm, let's square it. So you get AB, AB, right? But now by associativity you can take this BA, and that BA is again AB. And again you can take B square, A square, that is E. So we get order of AB is 2, right? But so it is not 4. So we get J is not cyclic because there is no element of order 4. So we get an example of a non-cyclic group which is abelian. So the converse is not true in general, right? So far we have seen, apart from those um, familiar groups, we have also constructed one abstract groups. But we'll see how, like, this group is also not that abstract. When we'll see direct product of groups, we'll see that this is basically if you take the Z mod 2, which is just putting n equal to 2 here, and if you take the product and you can give it a group structure, then we'll see this group. And so sometimes we call this group as Klein's 4 group. So yeah, so this is called Klein's 4 group, and it is sometimes generated by K4 or V4. So we'll see both these groups are basically same. Not exactly same, but basically we'll see they are isomorphic. So we'll come to it later. So maybe I should stop now, and next time we'll talk about this question, that how many generators there are for an infinite cyclic group, and then we'll see some example of a non-abelian group, some finite non-abelian groups. So yeah, let me